just in a little bit of a less sexy, but still crucial way.
The infrastructure of most large cities, the roads, the power grids, and the water pipes is aging, and in some places reaching the end of its lifespan.
Since these systems are basically a city's life support, we need to replace them. And if we can make them natural disaster-proof, well, that's all the better.
Safety glasses, everybody.
Let's start the cameras.
We're applying some small amount of initial compression to these load restraints.
Brad Wham is about to do some serious damage.
Very exciting, Justin.
Unlocking crosshead.
Recreating the conditions of a major earthquake.
The intention of this test is to take our pipeline, which is this blue PVCO pipe that's manufactured by a company in Canada, and we're going to impose it to a very large bending deformation that's going to cause it to deflect and bend at this joint.
Before they bend it, they'll fill it with water,
Pipes holding 80 psi.
simulating a municipal water pipeline.
We're going to apply internal pressure to this pipe of 80 psi, which is typical of water distribution systems around the country.
So the last time it went at 24 inches, approximately?
22.
Professor Tom O'Rourke oversees these recreations of natural disasters.
It could be an earthquake, it could be a flood, it could be a hurricane, it could be some sort of subsidence. Most of the time we're focused on earthquake survival or resilience, so that the water that's needed to put fires out after an earthquake is still flowing in the underground infrastructure or pipelines and conduits and can do the things that you need it to do when you need it the most. Christchurch, New Zealand was subjected to 4 major earthquakes from about September 2010 until December 2011. And each of those earthquakes destroyed its water distribution system and had to rebuild the entire system each time.
Ultimately, our goal here today is to provide the water industry with pipes that are more resilient to ground movements and earthquakes, specifically in the west coast of the United States, British Columbia, and a bunch of different areas. We're looking for better products, better solutions. Municipalities are looking for products they can use that are designed to withstand large movements. So this beam is going to move downward, make contact with this roller support, and the displacement is going to be imposed at this center section where we're going to have a constant moment region that is going to result in bending in the pipe. The intention of this test frame is to be extremely stiff and for the pipe to deform and bend as if it were being loaded under a worst-case ground rupture scenario. We think less about the larger earthquake and more about the specific landslide or fault rupture where a pipeline is locally crossing. So we're not getting resistance to the gauge. The gauge is still bonded to the pipe.
And the wires aren't touching each other, so they're not shorting out.
Right.
After all the sensors are connected and the water is turned on, it's time to begin the test.
Let's start the cameras. How do you like this for a loading rate?
Beautiful.
Contact. We have about 1,000 pounds in the system.
South support looks fine.
Pressure holding 80 psi. We've moved 2 1/4 inches.
No lateral movement.
Force is only about 700 pounds.
I don't see any issues at all.
2,000 pounds, over 900 kilograms, the weight of a small car, pushing on this pipe, simulating soil pressure during a major earthquake.
We have 50 or so real-time measurements going on during each of the tests.
They're measuring the strain on the pipe, internal pressure, water leakage, and how much movement is happening.
No indication of leakage.
600 pounds. Pressure's at 90 psi. We can go 1.5 more inches.
Is the force in the system?
1,000 pounds.
No leakage. Woo! Turn on the pump! We push the pipe 25 inches. That is equivalent to about 40 degrees of deflection.
This was a fantastic test. We had great response from the instrumentation, and from the pipe we got immensely large curvature, far greater than what we've seen in any other product. This pipe has the ability to accommodate large ground deformations through its ability to accept curvature and displacement.
It's all possible thanks to new materials and pipe designs.
We're seeing amazing things. Molecularly oriented polyvinyl chloride pipelines, when they reach the end of their lateral movement and then are restrained, they'll stretch in extraordinary ways.
That's all we can do.
Now they've got to get these results into the hands of people who can use them.
I am quite confident that our report will recommend this as a product that's qualified seismically.
Yep.
And so I think I can say that now that we've done the spending test, that it is a very viable option for water utilities.